Okay children, welcome back to the online tutor. So in this tutorial I'm going to explain uh, more examples with the friction lessons, right? The first example was in your screen now. A ladder whose center of gravity is at a distance b from the foot stands on a rough horizontal ground and leans in equilibrium against a rough cylindrical pipe of radius r fixed on the round. The ladder projects beyond the point of contact with the pipe and is perpendicular to the axis of the pipe. Let lambda be the angle of friction at both points where friction acts and 2 alpha be the ladder is suspended from a point at a distance x measured along the ladder from its foot. The ladder is limited in equilibrium at both points where friction acts. Show that b plus x into sine squared alpha cos 2 alpha equal r sine lambda cos lambda. Okay, the first thing is you have to draw the diagram. The ladder whose center of gravity is at a distance b from the foot stands on a rough horizontal ground and leans in equilibrium against rough cylindrical pipe of radius r fixed on the round. The ladder projected beyond the point on contact with the pipe and it's perpendicular to the axis of the pipe. Right, so let's look at the diagram, right? So we have a ladder and a cylindrical pipe, so it's look like this way, right? So the reaction of the ladder and the horizontal surface is r. So this is distance b, right? And this is x. The x mean the point where the external weight is added. So this is perpendicular, these are perpendicular because of the radius, and this is the reaction of ladder and the cylinder, right? So that S is field for the ladder. So the angle also given it's 2 alpha. These are perpendicular, right? So actually according to the law, the congruent triangles ADO triangle and ACO triangle are congruent, right? Therefore AC equal AD, this bearing alpha and radius is r, right? So therefore I'm just writing tan alpha equal r over AC mean r cot alpha, no? And can you remember they have provided us inequality, right? So the inequality was r cot alpha greater than b, right? So what's that meaning? So actually there might be the weight is located somewhere here and this is the external weight, right? So actually in my diagram b was wrong, right? So b should be, yeah, it's up to here. So actually b is less than r cot alpha, no? What is r cot alpha? So you can see according to my triangle A, this is mu r, right, the friction, and according to the triangle, so these are the frictions, right? F2 dash, right? So always the ladder is try to move to the down, no? Then the frictions are going up. So this is the concurrent position of the friction forces, right? So this is 2W. 2W mean the resultant force of the weight of the ladder and the external force, right? It should be in the middle of the way. This is 2W, right? Okay, so actually the r cot alpha is greater than b, right? So what's that meaning? So r cot alpha mean the triangle AD distance, no, so it's surely less than b. Right, now I'm taking moment around A. S into AD equal W into B. Sorry, it's not cot 2 alpha, it's cos 2 alpha. wx cos 2 alpha. Okay, we got a moment around A. So I'm just simplifying it. S into R cot alpha equal W cot 2 alpha B plus X, and pull W cot 2 alpha out. Then after I'm taking the vertical component of the ladder, right? So you just need to mention these angles. This is minus 90 minus alpha, then it's 90 minus 2 alpha, then the vertically opposite is 2 alpha. R plus S cos 2 alpha equal F2 dash sin 2 alpha equal, so I'm taking all upward forces, it's equal to 2W. So similarly, we can take the horizontal component as well. Mu r plus F2 dash cos 2 alpha equal S sin 2 alpha. So F2 dash equal mu s now. So I'm going to simplify it. So I just need to find the S value to substitute to the main equation, the moment equation, right? So here, if F2 dash mean mu s, no, I substitute it. R plus S cos 2 alpha plus mu S sin 2 alpha equal to W. So I'm just subtract first equation with the second equation multiplied by the mu. So here you can see mu r and mu s cos alpha getting cancelled. Then mu s sin 2 alpha plus S sin 2 alpha equal to W mu. So we can pull S out. Mu square plus 1 also same. Inside the bracket and sin 2 alpha it's outside. So this is the value of S. x, right? So we can now substitute s value to the main equation. Sine 2 alpha no, with mu square plus 1. So actually mu mean tan lambda, right? So in the theory part I told you that third equation, fourth equation, third is shifted to the fourth one. So now you can simplify it to take the final answer. B plus x sine 2 alpha. So all w's are getting cancelled. Cot 2 alpha mu squared plus 1 2 mu r cot alpha. So mu mean tan lambda no, mu squared mean 1, mu squared plus 1 mean sec squared tan squared lambda plus 1, then sec squared lambda. So I substitute mu squared plus 1 as sec squared lambda into cot 2 alpha. So actually it's not cot 2 alpha. In the beginning of the sum I told you it was my writing mistake. So this is cos 2 alpha, right? This is also cos 2 alpha. 2 mu mean tan lambda r cot alpha. So this is cos 2 alpha. B plus x sine 2 alpha sec squared lambda cos 2 alpha 2 sine over cos into r cos over sine. Sine 2 alpha means 2 sine alpha cos alpha, right? So I'm just simplifying it. So now we can cancel the common terms of the both directions. 2 so that's all, right? B plus x. So here sec squared lambda can be written in 1 over cos squared lambda. One cos is cancelled. Okay children, this is the answer of the question, right? So right, Okay children, this is my next example. A uniform solid hemisphere of weight W rests on a rough plane inclined at angle alpha to the horizontal, being supported by a light inextensible string attached to the highest point A of the sphere and to a point B on an inclined plane, as shown in the figure. The sphere is limited in equilibrium when the string AB is horizontal. Show that the angle of friction is alpha by 2 and find the tension in the string. So the diagram was given, but we have to include all tensions, weighted and the reactions all into the diagram, right? So we'll see how to do this. Okay, so first of all I draw the diagram they have given. So this is my reaction, this is the point of the center, right? So this is weight W, and the cylinder is trying to move to the down, then the friction is up. So this is the place of the all forces are concurrent, right? So this is tension T. So we'll see how to calculate this. These are perpendicular, no? So that once again these two triangles are congruent, alpha by 2, alpha by 2. So what is this? This is radius, so it's equal, no? Then the small angle, the triangle's angle is also same, it's lambda. The lambda means the friction angle, no? So we have to show so alpha by 2 equals to lambda. Okay, so this angle will be the small one angle is 90 minus alpha now. The whole one is 180 minus 2 alpha. And also it's equal to that, according to that small triangles, it's equal 180 minus 2 lambda. So each part will be 90 minus alpha. So same thing, so it's equal 90 minus alpha by 2. Because one small angle is alpha by 2. Therefore, lambda getting alpha by 2. Lambda equal to alpha by 2. So this is the first thing they asked, and we have to calculate the tension value. So I'm just considering the equilibrium of the cylinder. These are the forces, no? This is the resultant value. K. The weight is directly down. The tension also horizontal because they have given that. They mentioned that. So I'm taking so this is lambda, no? So I'm taking the component, x component and the y component. It's W equal k cos lambda. So T equal k sin lambda. So I'm going to divide these two. T over W will be tan lambda. So T equal W tan alpha by 2. So this is the answer of that. Okay children, so this is my next sum. A non-uniform rod divides center of gravity of gravity in the ratio 1 to 3 and weight W rest in vertical plane inside a fixed rough hemispherical ball. The rod is limiting equilibrium. Angle is theta. Inclined angle theta horizontal. The rod subtended an angle 90 at the center of the hemisphere. And the angle of friction is pi by 12. Show that tan theta equal 1 over 2 root 3. Okay, so let's see how to find that. The first thing is drawing a correct diagram, right? This is my hemisphere, right? And the axis is a rod. This is the center of the hemisphere. These are the reaction which passing through the origin. S and R. The friction force. So always the rod is trying to move to the down. Then the friction is this friction down. That friction up. These are 90 degree perpendicular. So actually the resultant is going up like this way. And another resultant which in this point is again, assume it's K1 and K2. Then the weight is directly down from that position. So it's W. So we just need to calculate the angle of the rod with the horizontal. This is 90 degree. The radius are same now, then what each one is 45 degree. So the small one is 5 by 12. It was given now. The larger one is 45. Then so that highlighted part is 5 by 6. It's 630 degree. So this is 1 to 3 ratio. No, it is given. The angle is 90 minus theta. Then cot 90 minus theta with the cot rule. ABE triangle 1 plus 3 cot 90 minus theta equal 3 into cot 5 by 6 minus 1 into cot. So we have to find that angle. It's 5 by 6 plus 5 by 4, 12. It's 5 by 3. Then 4 tan theta equal 3 cot 5 by 6 for root 3, 1 over root 3. Then 4 tan theta equal root 3 is single 3, 9. 9 minus 1 is 8. 8 over root 3. And divide by 4, it's 2 over root 3. So this is the value of the angle. Okay, children, thank you very much for being with us, and don't forget to subscribe my channel. So I will catch you with the third tutorial of the friction.